Hello everyone, my name is Babanisa Olaiwola. I'm here to make mathematics understandable as possible. Today's video is on determinants of a matrix. The video on the determinant of a matrix will be divided into three. The first will be the contributors to the determinant of a matrix, the methods to the determinant of a matrix, and examples of the determinant of a matrix. Determinant of a matrix is the scalar value obtained from the computation of elements of a square matrix that encodes certain properties of a linear transformation of the matrix. Determinant of a matrix can be denoted as determinant of A or with two vertical lines. Then determinant provides information about a matrix geometrically and algebraically. The idea of determinants did not emerge from an explicit goal of computing a single value. Historically, determinants were developed to help express solutions to systems of linear equations. The earliest contributors to determinant associated with polynomials, hence they defined the term determinant without any reference to the existence of a square matrix, which brings about the dual meaning of determinant. Determinant can be used to define the characteristic polynomial of a matrix and for checking the matrix invertibility. Therefore, determinant is non-zero if and only if the matrix is invertible and its linear map is isomorphism. The determinant is famously known for square matrices. Nowadays, there is an extension of determinant to rectangular or non-square matrices using Laplace expansion called determinoids. Other less known types or forms of a determinant are the Dodgson determinant, Freedom determinant, Slater determinant, Cauchy determinant, Cayley-Menger determinant, immanent, and functional determinant. The properties of determinants come from the characteristic of the matrices. Therefore, establishing the conditions for the existence of non-trivial solutions for systems of linear equation is the leading application of determinants. We start from the 16th century, the contributors to the theory of determinant. An Italian mathematician, Girolamo Cardano, gave a rule, which is a determinant method, for solving a system of two linear equations, which he called regular de modo, meaning the mother of rows. The rule later gave what we essentially known as Cramer's rule. In the 17th century, the concept of determinant first appeared in Japan through Seki Takakazu, popularly known as Sekikowa. In 1683, he published his finding without having a word that corresponds to determinant. Seki gave general methods for calculating determinant through a process he called tantam, meaning folding. In the same year, the European counterpart to work on determinant independently was a German mathematician, Leibniz Gottfried Wilhelm. His method involves the notion of permutations of symmetric groups and their signature. Leibniz used the word resultant for certain combinatorial sums of terms of a determinant and proved various results on resultants. In the 18th century, development on resultants or determinants was out of sight to mathematicians for over a century until a Scottish mathematician, Colin Maclaurin, in 1748 gave the first published results on resultant for solving 2, 3, and 4 simultaneous equations. Publication on his findings was made 2 years after his death. In 1750, a Swiss mathematician, Gabriel Cramer, hinted that determinants are useful in analytical geometry. Cramer gave the general rule for solving n-linear simultaneous equations in n unknowns by using his rule for determining the sign of from terms and for obtaining numerators. A French mathematician, Etienne Bezout, in 1764 gave methods of calculating determinant by combining his rule of term formation and his rule of signs into one. He then proved that the non-trivial solution of a system exists provided the determinant of the coefficient matrix is 0. In 1771, a French mathematician, Alexander Vandermonde, made known the theorem for expressing a determinant as an aggregate of products of complementary minors. He is viewed as the founder of theory of determinants, since he was the first to recognize determinants as independent functions. His method can evaluate the determinant of ordered n. Pierre-Simon Laplace, a French polymath, in 1772 gave a notion for a resultant or determinant and a rule for expressing a resultant as an aggregate of terms composed of factors which is minor, which are themselves resultant, and made a mode of finding the number of terms in this aggregate. Laplace expansion is one of the best methods for computing determinant, as it works for all forms of square matrices except it has a high computational time from the expression of numerous minors. In 1773, an Italian mathematician and astronomer, Joseph Lagrange, for the first time gave volume interpretation of a determinant. He treated determinants and applied them to elimination theory, which is the bilinear forms. He further gave a theorem that a minor of determinant adjugate to another determinant. For the 19th century, a German mathematician, Johann Carl Friedrich Gauss, while discussing quadratic forms, introduced the term determinant because the determinant determines the properties of quadratic forms. The new term introduced by Gauss was actually not determinant, but determinant of a form. Nowadays, the determinant of a form is referring to the discriminant of a quantic. In 1811, a French mathematician, Jacques Philippe Binet, gave an extension of a theorem of Lagrange on determinant which expressed that a sum of products of resultant as a single resultant. A French mathematician, Augustin Louis Cauchy, in 1812 used determinant to compute the volume of several solid polyhedra. First, he introduced certain matrix terminologies such as characteristic, principal terms, symmetric products, principal products, conjugate, and complementary derived system. Secondly, he gave a multiplication theorem for determinant. And thirdly, he introduced the idea of similar matrices, but not the term, and pointed out that the eigenvalues of symmetric matrices are real. In 1866, an English writer, Charles Dodgson, popularly known as Lewis Carroll, gave a method of computing the determinant of a square matrix by condensation. The method proves to be effective as well as minimizes the risk of miscalculation before arriving at the solution. The factor of Dodgson condensation defect is that the determinant of an interior matrix must not be zero. He was also the author of Alice in Wonderland. A French mathematician, Pierre Frédéric Sarrus, in 1842 gave a memorization scheme to compute only the determinant of a 3x3 matrix, termed Sarrus rule. Sarrus rule, or basket weave method, can be derived from the case of the Leibniz formula and Laplace expansion. Now, let's consider some methods of computing the determinant of a matrix. Some methods of computing determinant of matrix are fast and simple for lesser dimensions of matrix, such as minor method and Sarrus rule. For larger dimensions of matrix, we consider Schiel's condensation, Dodgson condensation method, Laplace expansion method, Gaussian elimination procedure, LU decomposition, KR decomposition, and Cholesky decomposition, although there are other methods also. For the minor method, let A be a 2x2 matrix with the entries A, B, C, D, then the determinant of A is given as AD minus BC. Let's consider an example to find the determinant of this 2x2 matrix. Then the determinant will be the multiplication of the diagonal entries minus the anti-diagonal, which is going to be minus 27 in this case. About the basket weave method or the Sarrus method. Now, the method is suitable for a 3x3 matrix, although there is a variation of the method to a 4 by 4 matrix. Let's consider this 3 by 3 matrix, and then what we're going to do is that we're going to introduce a slash line, then we'll repeat the first column and the second column. So it's going to be a 3 by 5 matrix. Now we are going to consider the diagonal and the anti-diagonal. So the diagonal, we're going to introduce plus sign and we draw an arrow facing down, while the anti-diagonal, the arrow will face up. Okay, now the next is that to get the determinant, we are going to multiply the entries of the first diagonal entries, then plus the second entries, the diagonal entries, will multiply all of them, and then plus the third diagonal, we multiply the entries together. Now to go to the negative part, now we are going to introduce a negative minus sign, then we also multiply the entries of the anti-diagonal of the first one plus the entries of the second one, we multiply them together, and the last entries of the anti-diagonal, so we multiply that together. So we are going to have this as our determinant. Let's use an example to back up our explanation. We want to compute the determinant of this 3 by 3. So the next thing we have to do is to introduce a slash line and then repeat the first column and the second column. Now, once we are through with that, we consider the diagonal entries first, which is in the red, then this anti-diagonal will be in the green. So let's consider the red first. We multiply 5, 3, and 8 together. Then we add it up to 1, 6, and 1. Then we add it up also to minus 4, 2, and 8. Once we are through with that, then we go to the anti-diagonal. And for the anti-diagonal, we multiply the entries together, 1, 5, and minus 4, then plus 6, 4, and 3, then plus 8, 2, and 1. Now, when we express this further, we are going to have our final answer to be 26. Let's consider another method which is called the Laplace expansion method. So suppose A is an n by n matrix, and then the determinant of this matrix is given by the summation of minus 1 to the power of I plus j, aij, mij, where minus 1 to the power of I plus j is positive when I equals j, or negative when I is not equals to j. Now, the minor mij is defined to be the determinant of the n minus 1 by n minus 1 matrix that results from the matrix by removing the ith row and the jth column, and minus 1 to the power of I plus j is the checkerboard sign. Then a complementary minor is the resulting n minus 1 by n minus 1 matrix diagonally adjacent to the minor matrix, while a consecutive minor is one in which the remaining rows and columns in the minor were adjacent in the original matrix. The expression minus 1 to the power of I plus j mij is known as a cofactor, and then the minus 1 to the power of I plus j can be represented in the checkerboard sign. The first entry, minus 1, I 1 plus 1, meaning that the I is 1, j is 1. The second one is minus 1 to the power of 1 plus 2, meaning I is 1, j is 2. And it continues to the last, minus 1 to the power of n plus n. Now, if we express this further, we are going to have plus, minus, for the first row, and it continues. The second row will be minus, plus, and it continues like that, depending on whether the n is even or odd. Let's consider an example, a 3 by 3 matrix. I want to compute the determinant using the Laplace expansion method. If we consider our expansion through the first row, then I is 1, j is 1 to 3. So the determinant will be in this form. And then we would cancel out the first row and the last row. So we are going to have a1, 1, minus 1, to the power of 1 plus 1, m1, 1. And that will be this. Then the next one is for us to cancel out the first row and the second column. And we're going to have it in this, and we express it further to be this. Because we are dealing with the first row, our expansion is with the first row. Now the last part we close the first row and the last column. So we have it in this, and then we continue to express this further to arrive at this. Our determinant will now be, when we express it further, for the first, for the second part, and for the last part, we are going to sum everything together. And if we do this, we are going to get determinant of A to be -1. This method to glance at is the Dodgson condensation method. Let A be an n by n matrix. After k-successful condensation, Dodgson produces the matrix below, whose entries are the determinant of all k plus 1 by k plus 1 contiguous submatrix of A, and we are given the determinant in this form. Note there are faster variations of Dodgson condensation. Adjacent terms of A are the expressed 2 by 2 consecutive minors of matrix A, which form n-1 by n-1 matrix. Let's consider this 4 by 4 matrix. We can express this in numerous 2 by 2 minors, and the total 2 by 2 minors we will have here will be 9, and all these 9 2 by 2 minors are referred to as adjacent terms. An interior of A is the n-2 by n-2 consecutive minor that results when the first and last rows and columns of matrix A are deleted. Let's consider this 4 by 4 matrix, and we are going to delete the first row, the last row, the first column, and the last column. So we delete the first row, the last column, the last row, and the first column. So the remaining matrix is what we refer to as the interior element. If we have only one, then it becomes an interior element, but in this case it forms a 2 by 2 matrix. Let us consider an example of a 4 by 4 matrix, and we evaluate the determinant by Dodgson condensation method. Now we are going to evaluate this into several minors, and all the minors we are going to have will be 9. So it's going to form a kind of a submatrix, and this is the way we get those minors. Okay, then when we find the determinant of each of the minors, we are going to have a 3 by 3 matrix. Evaluate the 3 by 3 matrix further into 2 by 2 minors, which is this. Then we compute the determinant of each of them, and we have that. Now the next is we divide the matrix by the interior element. If we divide each of these elements by the interior element, we are going to get the 2 by 2 matrix, and then we further to find the determinant of this 2 by 2 matrix. Then after that, we divide the result by the interior element of the 3 by 3 matrix, and when we do that, we are going to get 341. Let's consider some properties of the determinant. Determinant of an identity matrix is 1. Determinant of A is determinant of A transpose. Determinant of AB is determinant of A multiplied by determinant of B. Determinant of A plus or minus B, determinant of A plus or minus determinant of B. That the determinant is 0 if a column can be expressed as a linear combination of the other columns. Interchanging any pair of columns or rows of a matrix multiplies its determinant by -1. Determinant of CA is C to the power of n, determinant of A. Then determinant is 0 if two columns of a matrix are identical. Now you are going to try this exercise. You compare the determinant of the following matrices. After giving these questions, you are going to pause the video and then try the 8 questions, compute all the determinants. After that, you see whether your answer corresponds to what we have here. Are you ready? Okay. Pause the video now. Okay, the solutions are these. If you like this video, please click on the like and subscribe button for more videos, and don't forget to drop your comment below.